Direct's engineering school. His presentation is activity recognition in industry environment using tools learning. Welcome your presentation.
Thank you. Can you see my screen?
Yes.
All right. So hello everyone. My name is Robin Fay. I'm working at the Enalux College in Belgium, and I'm going to present you the research we have done with RIMS Lama, rented by the Grown project. And this project is the activity recognition in industrial environment using two layers learning. So the plan of my presentation will be as follows. I will start with an introduction and the state of the art. Then I will present you our approach and the evaluation of our algorithm, and I will end with a conclusion. So, the use of industrial robots is constantly increasing inside companies, and it can be used alone or with human beings, as you can see on the pictures, and it's called cobotics. So, in case of cobotics, it's important the robot clearly understands the movement of the human. Like this, it can react with the human being. And it can be difficult because there is a parallelism between the performance of the cobot and also the collect of the human information. And in more, there is also the safety, which is essential between the robot and the human being. Due to the evolution of cameras, algorithm of action recognition clearly improved. And in more, activity recognition, which is an assembly of actions, is more difficult because it can be composed of different actions. So now I will do a state of the art. So during the past few years, robots evolved a lot. So we can find now a lot of robots inside companies for interactive work with humans. And with this interactivity, it's essential for the robots to precisely understand the action and activities. So short reminder, an activity is an assembly of consecutive actions. A lot of algorithms exist for these recognitions, and during the past few years, it received a lot of attention. In these algorithms, there are algorithms based on joint skeleton and also on image. For instance, there is a recurrent neural network, so called RNN, which learns the long-term dependencies between features. But the problem is that we can have vanishing problems, and the vanishing problem is when the gradients of the neural network becomes too small. So we have now the long short-term memory algorithm, so LSTM, which appeared and is a variant of RNN, and it solves the problem of vanishing gradient problem. And also before using an algorithm, it is possible to use a temporal structure or also PCA, so it's the principal component analysis, which modifies the data by extracting the most important features of a bunch of data, but sometimes it can skip the most important information. We will see it later. So in this work, what we have done, we created a new activity data set, industrial activity. And how we did this, we did it by concatenating actions from the NTU RGB plus D dataset. And this new dataset will help workers in a cobot application. Then we evaluate this dataset with an algorithm based on LSTM, so long short-term memory. And finally, we propose the use of principal component analysis before the LSTM algorithm. So as a first stage, we created our dataset and we only focus on the 3D joints. So there are 25 from the head to the feet. And then we only focus on the temporal stage. So we have different frames. On the picture here, you can see 3 frames, and we take the difference of the position of the same joint between the frames. So like this, it will delete the size component. Then we resample it to 80 steps, so is the average number of steps of the whole data set. And like this, it will unify our data, and we will have the same number of data. Then we concatenate 3 actions for creating an activity, which means in total we will have 240 steps for each activity. And then finally, we created the 10 activities based on industrial context or environment. So here we have 3 actions every time, so for each activity. And for instance, we have starting, leaving, finalizing, which are activities we can use in an industrial environment. But of course, it can be extended or applied in other contexts. But let's have a look closer at the starting activity. So it's composed of 3 actions. So take off jacket, sit down, rub 2 hands. And we can see here on the picture below the person doing this activity at the several steps. So first, this person takes off the jacket, then sit down, and finally rubs 2 hands. So this basically represents the activity starting. Now, as an overview of our approach, we created 2 layers learning. So the first layer is the use of PCA we apply on each action, and then we have the LSTM before the prediction of the activity. So I will develop every layers. The first layer is the principal component analysis, so the use of PCA. And the principle of PCA is to dwindle the number of data. So how does it work? As input, we have our data, and PCA will analyze the data, and it will return the main components. So for instance, 1 component or 2 or 3, we can choose. It will return the main components of the data. And like this, it will reduce the training time. And in our work, we will varying the number of components from 1 to 10. As a second layer, we have our LSTM, so the long short-term memory layer, which is composed of a single LSTM layer. Then we have the dropout layer for reducing the overfitting. And then we have 2 dense layers, one with 100 output for interpreting the hidden layer. And then we have our layer with 10 output, which are our 10 activities. And then we have the classification, which is a categorical cross entropy loss function and hidden optimizer. So this part is for recognizing the activity. And it's 5 times repeated. Why? Because it's stochastic, which means we can have different output, and it will we will summarize our results. Like this, we can find our accuracy. We have 100 epochs, and the batch size is also of 100. Now I will discuss the experimental data set and also the protocol. So first, we just apply the LSTM on our dataset, and then as a second stage, we apply the PCA before the LSTM. So this is on the second stage, we have our double layer. So as previously presented, we created our dataset with actions from the NTU RGB plus D dataset. And this dataset is composed of 60 different actions And in these actions, there are individual actions and mutual actions, but we didn't take the mutual, we took only the individual actions, so with only one performer. So it was more than 56,000 videos recorded by 3 cameras, and the cameras provide the RGB videos, IR, the depth map, and also the joint skeleton. And we took the joint skeleton for building our algorithm. So there are 40 performers in total, and we took several performers for training and other for testing our algorithm. So now about the results. For the first part, so when we only applied the LSTM, we got here an accuracy of 95.5%. But then we tried to apply the PCA. So here we have our 2 layers. First PCA, and then we have the LSTM before the activity prediction. And we evolve the number of components from 1 to 10. And we can see here on the graph on the right, the accuracy according to the number of components. And if we analyze it, we can see for one component, so here, we had a result, an accuracy of a bit more than 70%, which is definitely lower than the LSTM only. But for a number of components higher than 1, so from 2 until 10, we can see we have higher, or we can have higher results than the LSTM only. And our 3 best results are for 9, 8, and 5 components. And for 9 components, we have an accuracy of almost 97%. But for further work, we will keep 5 components only because it will require less time for training the algorithm. And for 5 components, here we can see the confusion matrix, and we can see we have high results, except for dialing with somebody, which need to be improved. So for my conclusion, as a further work, we would like to collect a new dataset with more challenging actions in industrial context. We would like also to use the virtual reality to collect actions and increase our dataset, and also to test our approach on online recognition with sliding windows to detect the start and the end of a sequence, etc. And finally, we would like to test the performances of our approach on unbalanced datasets. Thanks for your listening. If you have any question, I will be happy to answer them.